Okay, good afternoon, guys. Let's begin our next week of classes. So I didn't upload the homework on the reinforcement learning because they updated the libraries and I need to spend a little bit more time to use the parameters from this Hugging Face reinforcement learning training. Data, they have a data set and training class. Hopefully, I will upload tonight the homework on our previous week. But it will be mainly just to run the code. So you won't even to write something, just to run and train and get some uh, results like generation aligned with reward model. Okay, so today, this week, we will talk about efficiency and efficiency in generation in during inference, efficiency during training model, storage, and so on. So a lot of aspects of running these large language models. So let's think about a simple model like BERT model, text classification, when we have input batch of sentences and our model returns the label, like if it's uh, uh, toxic lexic or not. So to make this lower. Okay. So to implement the model, we should consider three parameters. One parameter is the model size. The will it for how we will run our model? We will run it on the user's computer or on the server. So if we run this on the mobile phone, then maybe size is important. The second parameter that we should care about is the time of running of our model, which is called throughput. So maybe we don't want, for example, sometimes like in self-driving cars, we want to detect the pedestrians and we want that this model works online in real time. So this is maybe the one of the possible cases when we care about the inference time. And this third metric that we care about is called latency. So for example, if we ask ChatGPT, maybe we don't want to wait for a minute for the reply, and uh, this is called latency. So the first case, when we want to implement our model on the server and other devices will connect to this server, then the pipeline will look like this. Our devices will send requests to the server. Server has maybe one, maybe multiple models, and then it will return the output from the model on user's device. So let's just talk about a little bit about the hardware. So CPU, GPU, there's also TPU and FPGA. So what does it know the, of course, the abbreviation of GPU? What is the abbreviation of TPU? What does it stand for? Tensor Processing Unit. And what is that tensor in machine learning? Model tensors. Yeah, but what is the tensor in Torch? Yes, it's just a multidimensional array. And what is the difference between GPU and CPU? So on Google Colab, which processor we're using on Google Colab? GPUs or TPUs? But Google actually created TPUs, so we use TPUs on Google Colab. But what is the difference between GPU and TPU? It's an interesting history, and actually TPU were created by Google for translation task. So it's related to NLP. So when they wanted to implement the Google Translate, they calculated that it will be very expensive to run on GPUs, the model, and their engineers said, maybe we can implement our own processor so it will be more efficient for our task, which was the translation at that time. And this is how TPU appeared. So it's the it has the same idea of GPU, but it was created specifically for recurrent neural networks architecture and for neural network operations, because GPU is more general processor for graphics, and TPU works faster for neural networks. But because of what is called uh, uh, patent limitations, they can't sell their TPUs. So they can run the TPUs and the models on TPUs, but the patent, they have 17 years limits. So maybe in 10 years they will be able to sell TPUs. But I think at that time, the other architecture will be more popular. What is that? FPGA? Yes.
It's a field programmable gate array.
Yes.
So like
Did you use this for your embedded device or?
no, but I've used it for other like applications and on co-op.
Uh-huh.
It kind of like simulates logic gates, so it's more lower level.
Yeah, and what is the difference between GPU and
It's like a big difference. It's
but the main?
the main when you write code to run on a GPU, you're just kind of writing code, but when you write code for the FPGA, you're mostly making circuits.
Well, for machine learning, the main application is uh, parallel computations that you can make your calculations more efficient. For example, you can calculate gradients in, well, it's not the case of FPGA, but in general, how we train models in different devices. You can just upload your model on different devices and process one batch on one device, another batch on another device, and so on, and then aggregate the gradients, just average the gradients from all the devices. And as you remember, in the training code from Hugging Face, there is also parameter how many batches to accumulate, because as you remember, the large language models are better trained on large batches, but we can't process a large batch with limited memory. So you can just calculate several batches and update the gradient just after averaging like this 4 of 10 runs. So there is a parameter in trainer that allows you to use small batches, but multiple times. So it will result in a large batch. Yes. So but I think I'm not sure FPGA they have limited memory size. You can't
There's many different
many
sizes, so
different.
there's at some point a limit, yeah.
Uh-huh. But yeah, this is the more popular architecture, at least for image processing now. Okay, so we can run our model on the server. There are some pros, like you can run large models on the server. You can do this fast. There are also problems. For example, you don't have always connection to the internet, and when it can be a problem, like in case of self-driving cars, or just in case of cars, if it loses the connection with internet, for example, in tunnel, it still has to detect the object somehow. So in this case, you can implement the low quality model, a small model that you can run on your device. And when the connection is restored, we can again use the large model from the server. So let's answer these questions. What about the size, the speed and latency in case of this server implementation? What do you think the main limitation here? For example, is a size problem for a model? No, maybe not. Um, what about the evaluation time? So this actually could be a bottleneck because in evaluation time, we want to process data by batches, And to speed up the model, we will collect batches with requests of the similar length, because you remember how large language model works. It generates token, then runs again, generate next token, runs. You then need to run again model to generate the next token. And if you have a small input um, uh, prompt and a long prompt, then in one batch, then you will use padding and run your model by the length of the largest prompt. So here's the way how you can accelerate this. Just um, create a batch of the prompts of the size, maybe of the uh, prompt that is waiting for the largest for the largest amount of time, like for the oldest prompt. Because why should we take care of the uh, like time of the input prompt? Maybe because of the last parameter. Because if we don't, if we just aggregate our batches by the smallest length, then maybe we will never um, go to the prompt with larger length, and it will wait forever. So, okay, yeah, these are the priorities. Okay, this is I mentioned to group into batches. The other uh, acceleration is to use multiple servers, and for that you can use the built-in libraries like in TensorFlow or in Torch, like Torch Parallel, and it will choose, for example, what is the nearest server, and maybe send the data to the nearest server. You can write your own code for parallel computations. And of course, it will take more time to deploy. So, but maybe like for a large companies, it's important um, to spend more time on deployment and uh, make their models running faster. But for some startups, it's fine to use the ready packages. So second approach, the local inference. And um, how it works, the model will be uh, running on your device. And it means that every time you connect to the server will send the weights of the model to your device. And again, there are some problems. The size now of the model might be important, but also you need the connection to the internet, a fast connection to get these weights in reasonable time. There are other problems with uh, it's called when the company doesn't want to share the trained weights privacy. In this case, it's privacy of the company, not of the user. So maybe also that is one of the reasons why we don't want to run on the user device. But for example, for translation, maybe you don't have always connection to internet, and then it's a good idea to get some translation model on your device or in self-driving car when there is no connection with internet. And the third case is to run your model on the verb application. So in this case, the size will be really important. And there are several frameworks, like how you can run your models on JavaScript, for example, with TensorFlow, or what is the other? It's called um, ONNX format to save your model on. If you save this model on this format, I believe it's called ONXX, then you can employ this with arbitrary framework. Which format did you use for this sneeze recognition?
I just saved the weights and then I loaded it back in with I had two PyTorch models that were equivalent.
Oh, you use Torch.
Yeah, I used
You
Torch.
use Torch. Okay. So this ONNX model, it just saves the computational graph, and you can then use this computational graph with any framework. As example of such model, let's look at, I believe it's called Pix to Pix. So you can write image and process, and the model will upload weights on in your browser, and well, it's hard to see. I tried to uh, draw a longer tail. So yeah, this is example of the third approach. What do you think? What could be the problem with this third deployment? So I tried to use this model, for example, on my iPad, and it didn't work. So you will need to take care of all possible browsers, all possible um, uh, systems, and so on. So it's it looks like it's. Let's now think about efficiency and like money that company spends on running on the server or running on the user machine. So if you have millions of users, then it will be very expensive to use your own server. So maybe then it's a good idea to use user's device as for inference. But again, as I said, you will need to care about all possible device architectures, maybe. Um, okay. So this was about the efficiency um, of hardware. Now let's talk about efficiency um, in terms of the model. So did you hear about model distillation? What does it mean?
Your model, make a smaller model.
Yes. So, and one model is called teacher, another smaller model is called student. So, for example, uh, we have a large model that was fine-tuned, was trained or fine-tuned on some specific task. And then we can use, for example, drop some layers. For example, we had 12 transformer layers. We can drop, for example, half of layers, and we will get a smaller model. And we want to train a smaller model to perform on our task exactly the same as a large model. So how it's trained? We have input tokens, and when we pass these tokens to our main larger model, we will get logits. We will get probabilities of the next token, or maybe of the sequence of tokens. And then we can train our smaller model to return the same logits as a large model. And as you remember, the um, loss function that is used to make closer the distributions is Kullback-Leibler divergence. So the large model returns probabilities of the next tokens. The small model also returns the probabilities of the next token, but um, we will freeze the large model and we will train the small model. So the gradients will go only for the small model. And we will update the weights of small models such that the logits of this model are close to the logits of the large. So this is called distillation. And there is a comparison of distilled BERT with BERT and ELMO. Again, BERT is a very basic model, so maybe it's not a good comparison, but still, so in this case, they just used distillation for pre-trained BERT, not for fine-tuned BERT on specific task, just general BERT. And still was working better than the ELMA model. So in practice, the distillation works better for models fine-tuned on the specific task than for general BERT model. The next architecture compression is to use a smaller number of parameters. And as you remember, one of the possible case is to use matrix decomposition. Instead of one matrix, use the product of two matrices with smaller parameters. Or also use the matrix decomposition and, for example, a trainable nonlinearity between them. So another architecture compression is to use sparse matrices. So for example, drop 90% of the weights and from our one layer and use just 10% of weights. Um, so if you drop randomly some neurons from your layer, you should keep information about the indices of the dropped neurons, or maybe about saved used neurons. And this will increase the memory usage by 3 times, because you will need to store um, the index, for example, in 16-bit for every weight. Well, at least it will increase twice the size of the model. So there is the more clever way to save the information about the dropped weights. What do you think would be a more efficient way to store information about which weights were actually zeroed? The answer is to memorize just one number, seed. Because then you can reconstruct the dropped neurons indices if you know the seed. So then you don't need to store all the indices information. So this is okay, yeah, it's how to store sparse weights. You can only store the seed. So other approaches are using ensemble of models. So for example, use small models and aggregate their predictions. So it's called ensemble distillation. Um, so there was a recent paper where they used 1.5-bit quantization, but they trained many models and aggregated this very low um, it's called not resolution, the what's called like 8-bit, 4-bit. Um, what is the name for this? It just slipped my mind. Um, what's the name for data type like 16-bit, 8-bit? Huh? Well, float is the type, but what is called precision? Precision. Yes. So they used very, very low precision, 1.5 bit, and but to get the high accuracy, they used many models. So I'm not sure if it was better than to use just one model with 4-bit precision. So okay, the next approach is called accelerating by cascading. To apply um, like sequentially several models. I don't know how it's implemented in ChatGPT, but I can speculate that they train, for example, LoRa adapters on different tasks. For example, they could use one large model and train different adapters on different tasks, like one on the code continuation, another on just maybe question answering, and choose these adapters based on the some classification. So maybe they use another model for classification of the input prompt. For example, if we want to go to internet or if we want to use the code writing model, or maybe it's made with the same large model because you also can uh, write a prompt, like analyze the input text and fill in this JSON form, so for example, and then this is called also agents. Then um, they can use different models, or also um, people refer to this different agents. So the agent can use one model, agent can go to internet, and so on. So the same idea is in acceleration by cascading. When you have input prompt and um, somehow your model analyzes that you don't need a large model, then you can use a small model for continuation of this prompt. So you need an intermediate step to analyze the input, and based on this, use or large or small model. Um, Another approach, let's see. Yes, another paper proposed another idea. Instead of using different models, to use the outputs from different transformer layers. For example, we can get the logits from, let's say, second or fifth layer and just stop uh, evaluating our models. So we won't go to the last transformer layer. So this is another idea. But then they used classifier, and classifier actually was trained to understand if it was enough to use output from intermediate layer, or we should continue processing for our model till the end. And of course, what do you think if you train the classifier for this model, which says that you should stop, for example, on the fifth layer, or you should um, run the entire model, what it will always predict? Yes, it will always predict run the entire model. So they used also the regularization term, which penalized for using all the model. So this is another idea. Yeah, this is the illustration. You can stop after uh, going through 4 layers, transformer layers, or you can run your model till the end. Adaptive computation uh, time it's called. Um, Another acceleration was proposed to use. So for generation next token, to use every time different number of transformer layers. So, for example, here we use just the output from the second layer. Here we use the output from the third layer. But then it's actually a little bit tricky to keep track which layer you have used for generation, but it's also a possible architecture. And mhm. I have two more architectures, and next time we will talk about actually the quantization. So these are all approaches to use the same weights, but different model architectures. So let's say we have so the upper last approach is called speculative decoding. Let's say we have two models again, a small model and large model. The problem with generation, as you remember, for example, 1, 2, 3, 4, 5, that to generate 5 tokens, we should run our model 5 times. And of course, if you run a small model 5 times, it's less expensive than running a large model 5 times. So in this approach, we run our model to continue the prompt. So we get some logits. And after our model generated the text, we apply only once a large model on this generated text. Because when all the tokens were generated, then we need to run the large model only once. So after running a large model, we look at the probabilities of the generated tokens. If the probability of the, for example, first token, several, coincides with the probability from large model, then we accept the generated token from small model. Then we'll look at the second token, and at some point we will end up at the token for which probability of small model is different from the probability of the large model. And after that, we will use the small model again, which is called rollback. So we will change the prediction of small model, which didn't coincide with probability of the large model, and apply small model again. So this is the idea of speculative decoding. So so the main idea here is that we will use large model smaller number of times than the total number of tokens. Okay, so it also works for other sampling methods, not only for the argmax. So there is a paper that proves that. Okay, now I think it's the last for today. Yes, so what if we want, instead of dropping some layers, drop some neurons inside of the layer? So this idea is called uh, brain uh, brain damage, optimal brain damage. So, well, the first idea is to just drop neurons with small weights values, absolute values. But it's not always a good idea because if you think about linear regression, um, and if we don't use normalized input, sometimes the input feature can be, for example, thousands, and the weight very small, maybe 0.1, but the product will be still large. So if we drop just the weight with small magnitude, then maybe we will actually make our model worse. So yeah, the other idea is called optimal brain damage. And um, well, in linear regression, we could use lasso regularization, for example, to eliminate some weights. But here the idea is to use for every weight of our model to use sigmoid function like gating that will assign weights between 0 and 1. And this sigmoid function depends on some trainable parameters alpha plus noise, where noise is sampled from from a normal distribution. So um, if our parameter alpha is large, then sigmoid function will be close to 0, and the added noise won't actually make any difference because sigmoid of large number is pretty almost the same as sigmoid of large number plus a small number like 100. But if our learned value alpha is small, then maybe our training process wasn't pretty correct, and this additional noise epsilon will force our sigmoid function to be a little bit greater than 0. So it will be still small, but not very small, not just 0.1. So this is the idea of regularization in our neural networks. And here is the comparison. Another approach is called variational dropout. And here is the comparison between this regularization idea when we train additional parameters alpha, variational dropout, uh, random pruning when we just drop some uh, neurons with random seed, and yeah, you can see that they decrease the size of model and preserve the accuracy of this model. Okay, I think that's it. yeah. So I think that's it about models. And next time, yeah, so these are two main approaches. Or drop the layers, um, which is called structured sparsity, or drop some neurons, which is called unstructured sparsity. And yeah, there is also was another approach by NVIDIA to add zeros on the hardware level, but we will skip that. And next time we will talk about quantized bird. So, which is used in practice. Okay, that's it for today.